Hi, everyone, and welcome to lesson 17. So in this lesson, we're going to learn about friction. And so you're going to learn how to determine the amount of static and kinetic friction between two surfaces. And so we've already learned a little bit about static and kinetic friction as types of forces. So we'll go into a little bit more detail with that. And then we'll also apply the equilibrium model to it, like we did we started learning about in the previous lesson. And so the first thing I want you to think about is what actually causes friction? What is the cause of friction? Well, what we know is that on the microscopic scale, nothing is entirely smooth. So we know there's many things that feel very, very perfectly smooth, but there really aren't. At the microscopic scale, there's just all kinds of bumps and nothing is exactly flat. And so that's where friction comes from. And sometimes we actually want friction. For instance, if friction did not exist, then we would not be able to get our cars to start moving or stop moving. And so we actually need some friction in order to do that. And then sometimes if you live in the winter areas, then you know that it can get there's a lot less friction when there's snow and ice. And so we try to take advantage of this. We try to do some things. So most people who try to really get into it will do what we call studded snow tires, and essentially there's like these metal pieces in there that help to grip, give you more grip, apply more friction between the wheel and the road. Then there's also chains, which you don't see as much of, but that is possible, especially if you're so off road somewhere or working on a farm or something. All right, so that's what friction is, where it comes from. It could be useful depending on the type of field you go into, perhaps a type of mechanical engineering. You might be looking for ways to increase or reduce friction depending on the scenario. And so we learned there were two types of friction, static and kinetic. And so static friction is this force between an object and the surface that it's in contact with. And the point of it is that it's not moving. So the term static it is usually has a reference to something that's not moving, something that's at rest. And static friction helps to keep an object from moving, right? So that's the point of the parking brake in your car. It needs to be some friction so that the car doesn't go rolling off on its own. And it always acts, the direction it acts in is always opposite to the direction it would move if there was no friction. So for instance, if you parked maybe on a hill, if you didn't have the parking brake on, well, the car would roll down the hill. And so the direction that the static friction acts in is up the hill, right? Trying to prevent the car from rolling down it. Okay, so I have a figure here where I have a rope, maybe pulling this purple box, and let's say we pull it and we apply a force to it, so that would be tension. And I try to pull it, but it doesn't move. Okay, and it doesn't move because of that static friction. And so we can make a free body diagram in order to see that how the force of tension and static friction balances out the tension force. So maybe we would represent the box. We could make it as a box, or a particle is fine too. And let's say that I'm applying a force of 10 newtons, so a tension of 10 newtons to it, but it doesn't move. And so what we see happen is that the friction between the box and the surface it's on is also applying a force of 10 newtons. Okay, it's trying to hold it back. And if so, static friction always acts in response to whatever the applied force is until it reaches a maximum limit. So say the maximum limit, say the force that was required to move this box, let's say it's 30 newtons. Well, if I were to apply, we already tried 10 newtons, but if I tried to apply 20 newtons, the friction would hold back with 20 newtons, but it still would not move, not until we applied 30 newtons. And that's the point that we would overcome the static friction and the box would start to move. So kinetic friction is the force that there is between the object and the surface when the object actually is moving. And again, it still acts in the opposite direction. So in this case, now that it's moving, it acts in the opposite direction that the object is moving. Okay, it's like it's trying to slow the object down. And so what we see is that it's proportional. The force of friction is proportional to the normal force. And so we know that we have a weight, right? We've been calling it Fg for force of gravity, but we can use W for weight too if we want. And it's on a surface. If it's a flat surface, then the normal force is equal to the weight. And so that the frictional force, and usually we refer to kinetic friction as Fk, it's proportional to the normal force. Okay, and there's a proportionality constant, which we call mu, Greek letter mu, subscript k. Okay, so that mu is the coefficient of kinetic friction. Okay, and since it's a coefficient, there's no units. And for the most part, you usually will see a decimal. So what I mean by a decimal is that the coefficient mu k is typically, it's greater than 0, but less than 1. Okay, there are some weird situations where it does get above 1, but for the most part, and for what we're going to learn and deal with in this course, there's going to be somewhere between 0 and 1.0. So if you kind of get answer a problem and you see that it's like 20 point something, then or 1 point something, or anything above 1 or above, then you probably made a mistake. So that's a little trick that you can help keep handy in this course. So if the object moves, all right, so let's do a free body diagram. Let's say this is our box and we apply a force, all right. Let's say applied. That's our pulling force or tension in the rope. Okay, we can call it tension or whatever we want. And what happens is if we're pulling with at a constant velocity, then kinetic friction is going to be equal. Okay, it's going to be the same amount. So if we applied 10 newtons of force of tension, then friction is going to hold back with 10 newtons of tension if it's moving at a constant velocity. Okay, so that's what we've been dealing with so far with equilibrium, is when things are moving at or at rest or constant velocity. Okay, so in the next lesson, we'll actually get into when we're not moving at a constant velocity or at rest and we're actually accelerating. So for now, we're just going to keep it in that realm of equilibrium where we're at rest or constant velocity. So in these situations, then constant velocity, the tension is equal to the kinetic friction. Okay, and then going back to static friction. Well, we said that kinetic friction was Fk. Well, we refer to static friction as Fs. Okay, and so in kinetic friction, there's typically one value, right? There's just one coefficient of friction, but with static friction, it's different. There's not just one. So if you recall, when I showed you this, whether you pulled with 10 newtons or 20 newtons, if it required 30 newtons to move, well, then it could vary. So the static frictional force can vary between 0 and some sort of maximum, and it's at that maximum that the object will start to move. Okay, and so sometimes we'll call this Fs max. Okay, so there's a maximum value, and once you hit that value, that amount of force, then the object starts moving. But it will always respond only with the amount of force that is being applied to it to try to get it moving. So if you apply with any force less than that, nothing's going to happen. There's going to be no movement. And so the same kind of scenario applies as far as the normal force, and it's proportional, and that proportionality constant is mu s. And that's the coefficient of static friction. Okay, just like we had the coefficient of kinetic friction, we also have a coefficient of static friction. Okay, so kinetic friction only has one value. But static friction can vary. Okay, and you can actually try this if you want to take your iLab device, and it has on the bottom, it has some felt, and you can actually pull on the force sensor, and it works better if you put some more weight on top of it. And if you pull it, put it on a surface, and then you try to pull, it's a little tricky to do. So, but if you pull with enough weight on it, you'll actually see this difference. And what you'll see is you'll pull and pull and pull, and on the force versus time graph, it'll be messier than this, but it'll sort of keep increasing until you hit a peak, and then it'll sort of flatten out once it starts moving. And so this peak is your static friction. Okay, once you hit that static friction, then the object starts moving, and if you're pulling with a constant velocity, you'll get this nice, or essentially flat line. And so that's a way we can actually see the difference between that. And what we always see is that static friction is greater than kinetic friction. And so we can write that as mu s is greater than mu k. Okay, and you probably experienced this. If you ever tried to get something heavy to start moving, maybe at a heavy box on the ground, and you're pushing and pushing, trying to get it moving, you apply a lot of effort, but once it gets moving and you're pushing it along the floor or whatever, you find that it's not as it's not as much work. It's not as hard to keep it moving as it was to get it to start moving. And so that's the difference between static and kinetic friction. And so typically for any pair of surfaces, the kinetic friction is always less than the static friction. Okay, so for an example of that, let's say we have this box with a weight of 100 newtons at rest, and then it's pulled horizontally with 30 newtons of force. And we want to know, does the box move? And so we can see here that they've given us the coefficient of static friction and kinetic friction. And yes, static friction is greater than kinetic friction. All right, so So if we want to see, if we want to determine if the box will move or not, what can we do? Well, we know that if for at rest, we're dealing with static friction, and the relationship is that static friction, or the max static friction, is mu s times the normal force. And mu s here is 0.4. Normal force is, it's a flat surface, so it's just equal to the weight. So that's 40 newtons. So what that means is that we need, in order to get this object to start moving, to overcome static friction, we need to apply at least 40 newtons of tension or pull to this to get it to start moving. Well, if we, like the question says, we apply 30 newtons horizontally, well, we're not going to get this object to start moving. We need to pull with at least 40. Okay, so so now let's look at another one. We haven't dealt with Daisy in a while. So let's say we have a stubborn 120 kilogram Daisy sitting down and refuses to move. To drag her to the barn, the exasperated farmer ties a rope around her and pulls with a force of 800 newtons. The coefficients of friction between Daisy and the ground are mu s is 0.8 and mu k is 0.5. Is the farmer able to move Daisy? Well, again, we see that static friction is greater than kinetic friction, and sort of the same scenario here. We want to determine what do we need to apply, what force do we need to apply to overcome the static friction. So we could, if we want, make a free body diagram. She's on the ground. Well, then she has a weight downward. She has a normal force pointing up. We're applying some force. Let's say APP for applied. And then there's a static frictional force pulling backwards. So we want to know what do we need? What does the farmer need to pull with? How much force does he need to apply in order to overcome the static friction? Well, again, we'll know Fs max is the coefficient of static friction times the normal force. And we're given that coefficient here is 0.8. Normal force, it's on a flat surface, so the normal force is equal to the weight, which is mass times gravity. So 120 kilograms times gravity, 9.8 meters per second squared. And if you do that out, we get 941 newtons. And so in order to get this cow to move, we need to apply at least 941 newtons. So if the farmer applies 800 newtons of force, it's not going to cut it. The cow will not be able to move. Okay, so we looked at a couple situations of trying to overcome static friction. Let's look at some kinetic friction. So it's a snowy day and you're pulling a friend along a level road on a sled. You're walking at a steady 1.5 meters per second and the rope pulls up on the sled at a 30-degree angle. The mass of the sled with your friend on it is 60 kilograms and you're pulling with a force of 75 newtons. So what is the coefficient of friction between the sled and the snow? Okay, so a lot of stuff there. So let's break it down a bit. And so since we're dealing with a situation where we have equilibrium, it might be helpful to follow those steps of what do you do to tackle this problem. So if you have a way to do it that works for you, that's fine. But I like this way. It works for me. So I'm going to follow through this way. So the first thing to do, remember, is to make a diagram. Well, I found one and I stole it, so I didn't have to make it. So it's a good diagram to start with. And then we want to turn that into a free body diagram. So we have here some information given us that you're pulling the friend along a level road. So that means we're nice along a horizontal, the x-axis there. And that also means that our weight, let's represent the sled with just a dot, a particle. And so if we're on a nice flat surface, that means our weight and normal force are equivalent to one another. Okay, what else do we have going on here? Well, we have, we're pulling the rope on a sled at a 30-degree angle. So the pull is going to look, the force of the pull is going to look something like this. Okay. And we're also told that we're walking at a steady 1.5 meters per second. So we know we're moving, so there's no static friction. So we know that this has to be kinetic friction. And that's going to hold back opposite. Right? And the fact that it's steady is giving us the clue that we're dealing with a dynamic equilibrium situation, right? A situation where we're moving at a constant velocity, so the net force is 0. And so that's our clue that we can apply this equilibrium model. Okay, so all right, so what do we have here? So we can now, our next step is typically we want to figure out what the net force along each axis is. So we can say, well, what's the net force? The x component of the x component of the net force. Well, we're going to have, let's see here, the normal force, weight, and kinetic friction, they're all perfectly along an axis, so that's nice. The only thing that's not perfectly along one particular axis is the pull. So we have to break that down into its components. So we're going to have an x component, okay, of the pull, and a y component. And we know that this is 30 degrees. Put that in there. And okay, so now we can find out we can make some equations to represent this situation with a net force equal to 0. So we know that we have along the x-axis, we have the force of the pull, the x component, minus the force of kinetic friction, and that all has to equal 0. Okay, so that means we could say that the force of the pull, the x component, is equal to the force of friction. Then for the y, our net force along the y-axis, well, the normal force is up. The y component of the pull is up, and then the weight is down. And that all has to equal out to 0. We could simplify that a bit. We could say that the normal force plus the force of the pull, the y component, is equal to the weight. Okay, and so we did a little bit of simplifying. And so what kind of things do we know? Well, we know we have that pull is 75 newtons we're given at a 30-degree angle. So we're given that much. We're given the mass of the sled with your friend on it is 60 kilograms. So that means we can figure out the weight is 60 kilograms times gravity. So I get 588 newtons is the weight. And that's not going to be the normal force though, because the pull is not perfectly horizontal. It's partially vertical as well. That means part of that force is actually partially lifting the sled. So the normal force is not equal. The surface is not pushing up perfectly because you have a little help from that pull. Okay, and so what do we want to know? Well, we want to know what's the coefficient of friction between the sled and the snow. So it'll be the coefficient of kinetic friction. So we have one expression that we made where we have kinetic friction there. So maybe we could start with that. And we can rearrange. We know that kinetic friction is mu k times the normal force. And that's equal to the force of the pull, the x component of the force of the pull. So what's that x component? Right, well, we know the x is the cosine of the angle. So this is going to be f for the pull cosine 30 degrees. Okay, and so then mu k is just the force of the pull, which is at 75 newtons, times the cosine of 30 degrees divided by the normal force. Okay, so we have most everything, we just don't know what the normal force is. Well, perhaps we can figure that out since the other expression that we created does have the normal force in it. So let's solve for n, and we get weight minus the y component of the force of the pull. We know that the weight is 588 newtons. The force, the y component of the force of the pull, right, is this guy here. So that's going to be F sine 30 degrees. Okay, so 588 newtons minus 75, and the sine of 30, remember, is 0.5. Okay, and I get about 550.5 newtons is the normal force. Okay, and it's less than the actual weight of which was 588 newtons, which we should expect because there was that partial lifting of the sled. Okay, so now we know the normal force. We can go ahead and finally finish calculating our coefficient of kinetic friction. Cosine of 30 is the 0.866. And the normal force was 550.5 newtons. Our units will cancel, which is what we want. And I get about rounded to 0.12. Okay. So that's the coefficient of kinetic friction between the sled and the ground or the snow. Okay, so a few more problems that are going to be related to friction. These kinetic static friction, applying that also goes to the equilibrium model. And one more homework or one more extra example problem on Moodle, if you want to check that out, if you want to some more practice with this. And so did we learn to determine the amount of static and kinetic friction between two surfaces? So we know we have that the frictional force is proportional to the normal force. And as we saw in the last example problem, the normal force is not always equal to the weight. And also we saw that the coefficient of static friction is always greater than kinetic friction. It's easier to start something moving than it is to keep it moving. Okay, and that's it for lesson 17.